Consider the vaporization of liquid water to steam at a pressure of 1 atmosphere. A, is this process endothermic or exothermic? Well, if I'm going to go from a liquid to a gas, I have to put heat in. It'll be endothermic. So a positive value on delta H. What temperature range is this reaction spontaneous? All right, so spontaneously, liquids change into gas at 1 atmosphere pressure, anything above 100 degrees Celsius or 373 Kelvin. In what temperature range is it non-spontaneous? So below 373 Kelvin. All right, so it's not going to happen below 373 Kelvin. You're not going to get liquid water going to the gas phase. I mean, you'll have a certain number, but it won't be spontaneous, right? So I've got to get the temperature up to 373 Kelvin to spontaneously go into the gas phase, right? Lose most of my liquid, turn it into gas. At what temperatures are the two phases in equilibrium? Well, at this temperature, right? So at this point, the rate of condensation is equal to the rate of vaporization, right? So we have an equilibrium established here between going into the liquid phase and the gas phase. Express the second law of thermodynamics in words. Okay, the definition is, for a spontaneous reaction, the process for a spontaneous process, the entropy of the universe increases. The universe. And for a process at equilibrium, the entropy change of the universe is 0. All right, the universe is hard, right? That's everything except for the system. So there's a relationship between what happens with the system and what happens with the surroundings. And the way we equate how disordered the surroundings becomes is by looking at the delta H of the system. All right, so if we have an exothermic reaction, that means that the system is losing heat to the surroundings. If you put heat into the surroundings becomes more disordered, right? The temperature goes up. If we're going the other way, endothermic reaction, you take heat out of the surroundings and put it into the system. That means the surroundings becomes more ordered, right? The temperature slows down. So with this said, we now have a term that we can plug into for delta S of the surroundings, right? It's related to delta H of the system divided by T. And if we rearrange this, this is where we get delta G is equal to delta H minus T delta S. Right? It's by referencing the second law of thermodynamics. So if we have B, if a entropy of the system increases in a reversible process, what can you say about the entropy of the surroundings? Well, it must decrease, right? So there must be a point where we come to equilibrium, right? The forward rate of reaction is equal to the reverse rate of reaction, and we're not changing the entropy of the universe anymore. So loss of the increase in disorder of the system has to be equal to the increase in order of the surroundings. In a certain spontaneous process, when the system undergoes an entropy change of 42 joules per Kelvin, what can you say about the surroundings? Well, if we're becoming disordered to this magnitude, that must be the magnitude that the surroundings is being ordered. All right, so if the surroundings is becoming more disordered, the surroundings must be becoming disordered. Must be becoming ordered. How does the entropy of the system change when a solid melts? Well, anytime you lose a solid, you're becoming more disordered. A gas liquefies. Gas is the most disordered system, so if you're losing gas, you're becoming more ordered, right? You're losing disorder. Subliming is going from the solid phase to the gas phase, so again, becoming more disordered. Predict the sign of entropy change of the system for each of the following reactions. So I'm looking at A, right? I've got 1 mole of nitrogen gas reacting with 3 moles of hydrogen gas to make 2 moles of ammonia gas. Anytime we lose moles of gas in a reaction, you're losing disorder. So the sign on delta S is going to be negative. Solid reacting to form a solid and a gas. Again, we're making gas. So if we're making gas, right, we're making a mole of gas here. Producing gas means you're becoming more disordered, right, and your entropy is increasing. Looking at C, 3 moles of gas making 1 mole of gas. We're losing moles of gas. So the sign on delta S is going to be negative. And with D, you've got 3 moles of gas going in, 3 moles of gas coming out. So we don't know. We're not able to figure out what the change in delta S is just by looking at the equation. So the things you look for an increase in entropy is gas being produced and more particles being produced. I don't see anything like that with D, so I don't know what it's going to be. What is the meaning of standard free energy change, delta G naught, as compared with delta G at non-standard conditions, or delta G absolute? Okay. Free energy changes at standard conditions are when we completely convert reactants into products, all right? So we're saying that if we took reactants and completely lost all of our reactants and turned into products, this is what the free energy change would be for the reaction. All right, so we can look up free energies of formation of the products, we can look up free energies of the reactants, just like we did with delta H, and figure out what the change in free energy at standard conditions would be. We can use this then to equate to equilibrium constant. All right, so if we have a negative value for delta G naught, that's going to be a big K value. If we have a positive value for delta G naught, that's going to be a non-spontaneous reaction and a small K value. So negative RT, R is the gas constant, T is in Kelvin, can be equated to the natural log of the equilibrium constant. When we're talking about free energy changes at non-standard conditions, this is what we use to determine position of equilibrium. Are we at equilibrium? Are we before equilibrium? Or are we past equilibrium? So if we have a negative value for delta G absolute, it means we're sliding towards equilibrium. When delta G absolute is equal to 0, it means we're at equilibrium. And if delta G absolute is positive, it means we've gone past equilibrium. So there's a relationship between G absolute and G naught, right? If I add RT natural log of Q, the reaction quotient, right, we can plug in the concentration of the products and the reactants into Q and see how we compare to G absolute. Again, if we have a negative value, we're going towards equilibrium. If we've got a 0 value, well, those were equilibrium concentrations. We're at equilibrium. And if the Q value is greater than it should be, we're past equilibrium. And the value on G absolute would be positive. Blah, blah, blah. B. For any process that occurs at a constant temperature and pressure, what is the significance of G absolute being 0? Well, we just said it. It means you're at equilibrium. C, for any process where delta G is large and negative, what does this mean? Does this mean the process necessarily occurs rapidly? No, there's no relationship between rate of reaction and free energy. Free energy is about equilibrium. All right, so a large G absolute value means you're at the beginning of the reaction, right? A large negative value means you're just sliding towards that 0 spot where you're at equilibrium. So going back to our graph, right? Free energy plotted against extent of reaction. 100% reactants on the one side, 100% products on the other. I start with all reactants. I have no products. So as I go towards equilibrium, all right, so again, if we wanted to get the difference between the reactants and the products, that's what G at standard conditions is, G naught. All right, so G naught can be equated to, hey, where do you end up in this reaction? Do you end up making more products than reactants? We can look at the magnitude of G naught to equate to equilibrium constant. But if we're looking at the line, this is a loss of free energy at non-standard conditions. All right, so I'm losing free energy, losing free energy, losing free energy until I don't lose free energy anymore and I start going back up. When I bottom out, this is when the reaction's over. And where did I land? I mean, extent of reaction. Am I more towards the product side or more towards the reactant side? If I've made more products than I have reactants at the end, this would be the curve for a spontaneous reaction. So when delta G absolute is 0 and the reaction stops, you've mostly got products and less reactants. So this is what I found off the web, right? It's the same thing. We're losing free energy, right? So we've got negative values of free energy until we have a 0 change in free energy at non-standard conditions. Okay, and if I'm looking at this being a spontaneous reaction, the change in the free energy of the its standard conditions for the products versus the reactants, I'd get a negative value, which implies that when this stops, I'm more towards the product side, as opposed to this one, whereas I look at the change in free energy of the products versus the free energy change of the reactants at standard conditions, I'd have to put free energy in order to go all the way across. So this implies a non-spontaneous reaction. So as I slide towards equilibrium, losing free energy, the reaction stops well short of making a lot of products in this situation. And at this point, at point 3, your delta G absolute value is 0. And if we take the difference between the delta G at standard conditions for the reactions and the products, I'd have a positive value. Again, it implies that I've stopped the reaction not very far after I've started, right? Before the reverse reaction stops it, and then I'm at equilibrium where I have a lot of reactants left over and very little products formed.